Hello everyone and welcome to the last video in the near smart contract security series. And in this video we'll go over tips and best practices when it comes to near smart contract development and security. The first thing is we don't have to use state assertions in initializers because we already have init macro which does exactly that. So if you expand init macro, you'll be able to see that it already includes the check which checks whether the state exists or not to prevent anyone from calling initializer again. So the next thing is missing zero value checks. We always have to make sure that we cover any cases where we get zero inside of argument or during the calculation, because if we, for instance, doing division and we receive zero as a denominator, we might get a crash or panic. So, but mainly we want to assert that the value is not zero because we don't want to perform redundant operations, because usually operations performed on zero are redundant in the majority of the cases. And in addition to this, obviously, we don't want to have zeros around, especially during calculations, because they might introduce some severe logical bugs. So the next thing is unchecked attached deposit. So functions marked as payable can accept the attached deposit since they don't have a check that prevents it. So there is no check which checks whether someone attached a deposit while making a call to a certain function if the function marked as payable. So you can send money to that function. And in Solidity, there is a trick to just mark something as payable to pay less gas because there is no additional check. And when it comes to near, it does not provide any visible benefits. So using it for optimization purposes doesn't make any sense. Therefore, if we use payable, we always have to check attached deposit, or we have to be sure that we are planning to do something with that money. Otherwise, if we just mark something as payable, we just increase the possibility of someone accidentally sending money to our contract, which is not good. So usage of take. When take is used on option and lazy option types, it deletes the value and replaces it with none. So we should be very careful when we use take, since it takes value and then deletes it afterwards. So if we, for instance, want to get, I don't know, token metadata, and we get it using take, token data will get deleted afterwards. So we should always prefer using get instead for those types. So as in this example, we get lazy user option data, which gets data from the lazy option and the regular option. So we do self option data take. We basically get the user data, but then that user data will get deleted. Require. So there is assert, and since SDK version 4.0, we also have require. And require does not include any Rust specific data in the panic message. Hence, it decreases the code size and obscures the exact place of error. So it might be more useful for us to use in production setting, especially if the project is closed source. Maybe we want to obscure the exact place of error. All right, that's it for require. And let's move on to tautological expressions. Those are expressions which always satisfy a specified conditions or are logically redundant. I've seen them a lot. So the most common one is when we're using unsigned integers, but we still check whether the value is less than 0. So we're asserting that the value is not less than 0. It's already unsigned integer, so by definition cannot be less than 0. So it's redundant. And another example is checking that the value is larger than 0. It might not look obvious, but in case of unsigned integers, if our purpose is just to check whether the value does not equal to 0, we should do that. Usually, if in other languages, if we were operating in signed integer space, then the assertion whether the number is bigger than 0 makes perfect sense because it can be less than 0. But in case of unsigned integers, the only thing we need to check whether the number does not equal to 0, because by definition it cannot be less than 0. So having a check which checks whether the number is larger than 0 is redundant. So the only thing that we need to check whether the number does not equal to 0. And by definition, other numbers are going to be larger than 0. And also as spotted a real-world tautology similar to the example I explained before in the near SDK. You can just click on that link to check it out. Okay, so two-step ownership transfer process. So when we want to transfer a role to someone else, it's necessary to take precautions against human error. It's not enough to just check the grammatical validity of the account, because it's still possible to just mistakenly transfer ownership to a valid account. So we can just mistakenly enter a valid account that ownership of the contract might get transferred there. So that's why we should implement two-step ownership process, and it can work like simply as owner proposes a new owner to propose function, and new owner goes and then just accepts ownership. So it's super easy, and it decreases the possibility of human error to a minimum. So the next thing is lack of pausability. We cannot be 100% sure that our contracts are safe, secure, bug-free. Unfortunately, that's not the case. We cannot just guarantee this. That's why we should implement some safety measures such as pausability in our contracts. So in case of any bad events happen, to have some sort of damage control, we can just simply call pause main functionality, so that no one, if it was just a regular bug, users won't get disturbed or lose some money. If it was malicious attack, hacker won't be able to exploit our protocol further. So it can be implemented simply having a state variable, keeping track of status, which is like isPost, creating a function called toggle post to flip isPost from false to true and vice versa, and asserting whether isPost is false at the beginning of each function. Can be encapsulated in a separate function, and throwing an error if isPost is true. So it's pretty much it. It's super simple to implement, and it will save, and it can potentially save your protocol. So let's move on to the JSON type. So that one is interesting. Near has two types. There are JSON types and the regular types. JSON types are usually denoted with a capital U, and for instance, we have unsigned integer JSON types and regular unsigned integer types. And the reason we have those is that when we accept data from a user, we take data in a JSON serialized format and then deserialize it into regular unsigned integers if we accept unsigned integer. And when we output data, we serialize it into JSON and then output it in the format of unsigned integer, in the unsigned JSON integer type. And the reason we have all of this is that JSON type has max safe integer, which falls in the range between -2 to the power of 53 plus 1 and 2 to the power of 53 minus 1. So, and the max safe integer is this number. And if the value that we get from a user, and because we're getting a value in a JSON serialized format and then we deserialize it, if the value is larger than that, it can cause some super weird behaviors, and it might lead to super critical logical mistakes. So for instance, if we get max safe integer and add 1 to it, and then add 2 to it, and then assert that it's going to be, both of them are going to be equal. That shouldn't happen. So basically what happens is when we, for instance, if we receive this value +1 or this value +2, let's say from a user, but when we deserialize it, that value in both scenarios is going to be the same. And there are also weird behaviors. If we like for the last 4 digits are going to be 1, those after parsing it's going to be truncated to 0. And with the 7s, it's the same thing after parsing. So all of it can lead to severe logical and miscalculation bugs. So to prevent it from happening and still use numbers larger than 2 to the power of 53 minus 1, aka max safe integer, we should input and output data in a string format, not accept in a regular format, but actually accept in a stringified format, meaning that argument should not accept just a regular unsigned integer, but should accept JSON type unsigned integer. So not U128, the small u, but actually large U128. So if we try to input non-string value to a function that expects U64, U128, we will get an error. So user won't be able to just simply input like a regular unsigned integer. It has to be in double quotes. So, and we should use JSON types as types for values which may be larger than the max safe integer. And we should also return the data with a JSON type. Imagine we're gonna receive the data, then we're gonna serialize it to a JSON type, and then output it to a user. So if the value is larger than safe integer, it might cause at the simplest like issues in the web app, in the front end, because if we are reading that through a getter, it might cause some bugs on the front end. So here is an example. If we accept an argument using JSON type but return value using regular types, to be completely safe, we should accept and return values using JSON types, so that in all steps, our value is correct. It's not getting truncated or it doesn't cause any weird behavior. So during the serialization of this value, we get a correct value back because we accept argument using JSON type. So the argument, the function that accepts this value actually has the U64 or U128 in the argument, not a regular one. So this one is going to be stringified. And during the serialization, when we decide to actually return that value through a getter to a user, to a web app, whatever, in that scenario, since we are not using the JSON type, but the regular type, such as U64, U128, the value becomes that, which is totally incorrect. And another example, we accept an argument using regular types, but return value using JSON types. So during the serialization of this, it becomes that value, which is not correct. User sends us this super large value, but during the serialization of JSON, we get this thing. And it gets assigned to a variable, and during serialization, we just, even though we're using a correct JSON type, since the value is incorrect, we just basically stringify it and serialize it and return it to a user. But since in the beginning it was incorrect, we just return incorrect value, even though we're using a correct JSON type. So, and here is an example. We just have a simple function. We have just a count JSON, which is U128. And then we insert data using U128, but view using U big JSON type U128. It's incorrect. That's the second example I explained before. And this one is we get data using U128, but return value using a regular U128. And this one is the first example I showed you. So we accept argument using JSON type, but return value using regular types. And this one is correct one. We get data using U128 and we view data using U128, as you can see from here. And in this scenario, everything is going to be correct. So here's an example if we run it. So we just have insert data, and we're inserting this data. Basically, we're inserting, this one is for the first example. So we're getting this value, and then when we're viewing it, we're getting incorrect value back through here. All right. So let's move on to the next topic. And this one is two-factor authentication. So Near has two types of access keys. There is like a full access key, basically do whatever you want, just call functions, transfer money, create, delete accounts, whatever you want to. And there is also function call key. And this key lets you only call specified smart contracts functions that do not require deposit. So when a user interacts with the smart contract through website, the website gets a function call key to interact with smart contracts on behalf of the user. And imagine if the website gets compromised, and now that website can call some function on behalf of the user. And to protect against that, 2FA can be used in super crucial functions. And 2FA is triggered when we try to attach a deposit to a function call. So, because regular function call key cannot just transfer money from your account. If we just assert super minuscule amount, it will still trigger 2FA, so the user has to actually sign the transaction with a private key. And hopefully attacker doesn't have a private key, so nothing will happen. So we can use assert1 yocto in crucial functions like transfer tokens, so that even if the website is compromised website won't be able to just simply call the transfer tokens, since we have assert1 yocto, and user will get prompted to sign a transaction. All right, that's it for this course. I hope you liked it, and I'm also thinking of creating additional content and keeping this course up to date. I already have some thoughts about creating a video about collections in Near, like a nested collections, or just how you should be using them, because I spotted several bugs, that super severe vulnerabilities that came out of incorrect collection usage. So I'm planning to also record that video. But as of now, that's the latest video in this Near smart contract security course. I hope you liked it. And if you liked it, just click a like button. So yeah, just click a like button and subscribe, and yeah, subscribe to my socials also, because I'm sometimes adding some cool tips and tricks about like security, programming. Yeah, just do all of this, and thank you for watching this course. See ya.